So welcome back to the series of dynamic lectures. In today's video, we will look at the derivation of the normal and tangential acceleration. Okay, so let's start off as usual with position. Okay, as in any dynamics concepts or problems, you will always start off with position or coordinate system. It's a curvilinear motion. We will put our position of the particle along the curve, right? Let's put an origin there. And we see our position can be represented by letter S. We can represent the unit vector, okay? It's moving in a 2D space. So we will have the unit vector in the tangential direction. So the tangential direction is always tangent to the curve. Okay, remember a circle. The tangent at this point is this way. The tangent at this point is this way. And the list goes on, right? Right. We also have the normal direction, and that will have a unit vector of u sub n. And a unit vector has this arrow mark on the top, because it is a vector, a unit vector. Let's see the velocity. All right. Velocity is active only in one direction, which is in the tangential direction, right? So it is understood that v is in the tangential direction, and that is well understood as, the velocity vector. There's no normal component, so, we may as well omit the sub t here. As always, in any vector, it must have magnitude and direction, okay? The magnitude is the v itself, velocity itself, right? And the direction is going to be the direction vector, the unit vector in the tangential direction, u sub t. Now this, let's box this one. So now let's move to the acceleration, right? We have position, we have velocity. The next in line will be acceleration, right? So acceleration, right, is basically the time derivative of the velocity, right? The velocity vector, Now, you see, this unit vector is always changing with time, right? If you consider the particle that has moved to this point, right, it will have a different direction of the ut, right? And this is going to be your un, of course. But the point is, as you, travel across time, right, the u sub t will always change. Right? It will always change. It cannot be treated as constant. So now what that means is we have to treat this as a product rule, right? Remember your product rule in your calculus. When you have multiplication of two functions and you take the derivative of that multiplied function, that's going to equal this one, right? The first function times derivative of the second function plus the second function times the derivative of the first function, right? A is going to equal, F is basically your velocity. G prime is the unit vector dot, dot represents the derivative, the time derivative, right? Plus G will be your unit vector times the F prime. I'm going to write the F prime, which is V dot over here, right? Great. So we now have the equation that becomes the basis of acceleration in the normal and tangential direction. Okay? Now, if I simplify these two unit vectors position, right? And I say, okay, let's have this one as the first u sub n, and then that one as u sub t, right? They are unit vectors, they have an arrow. And then we will have our u sub t the second one, let's mark that as, oops, okay, u sub t prime, right? Okay, the final position. Now, there's going to be a differential of the unit or the vector unit in the tangential direction, and that's going to be dut, right? So you see this u sub t, you add with the small differential of the unit vector in the tangential direction will result in the final unit vector in the tangential direction, right? And at the same time, you will have a small angle differential here. Now, we are going to use the concept of the segment of a circle. Okay, let's say we take an arc and then there is a radius. Okay, we say this small segment is S. So we say S equals to the radius times the angle. So if we apply this formula, right? This formula, S equals R theta, into this figure, right? We will see that S, the small segment here, is actually this small segment here, DUT. Okay? It is so small that it appears as a straight line. And the theta is d theta. Okay? And the R is going to be the U sub t prime. Now let's put that into equation. So all these are magnitude, right? So let's put the magnitude dut equals ut prime times d theta. All right. Okay, remember this is magnitude. So I'm going to put the magnitude sign here. Okay. And you know the magnitude of du sub t is just du sub t. And the magnitude of u sub t prime, this is a unit vector. Okay. This will be a perfect unit vector, which is 1. And we will multiply that with d theta. Now, this is just the magnitude, right? Okay, so the magnitude, sorry, this magnitude should be without the arrow. Okay, right. So this is magnitude. And let's translate this into a vector. Okay, the vector form will be du sub t, put the vector. It must have a direction, right? So that number 1 has been cancelled out. What is the direction of du sub t? Okay, if you notice, the direction is just the same as the u sub n, which is the normal direction, right? So let's put that here, direction. And now let's take the time derivative. The time derivative, okay, we take the time derivative of the entire thing. That's going to be du sub t dt equals d theta over dt, and the direction of the vector is in the normal direction. That gives us u sub t dot equals to theta dot. Okay, let's not forget our unit vector u sub n here. Let's scroll a little bit. Now you will see why these steps are useful, right? Okay. This u sub t dot is actually your u sub t dot over here, right? So you are going to substitute this thing into this expression. And what you'll get is A equals V times this entire thing, which is theta dot times the normal direction vector, plus you're going to copy everything down, V dot times u sub t, which is the tangential direction. Okay, if we rearrange everything, acceleration will become V dot in the tangential direction plus V theta dot in the normal direction. Okay, let's put the direction of the vector. Now we're almost done. Okay, for the radius of curvature, right? I'm just going to copy the position vector here. Let me just copy this image, right? Okay, and then we paste it at the bottom. All right, so to put radius of curvature into perspective, right? We will draw a line from the particle to an arbitrary distance. Okay, so that will be the distance or the radius of this curve. Okay, and that radius is called the radius of curvature. Now we have the radius and we have the S, right? Okay, the small path taken from origin to this position, and we can adopt the same formula, S equals r theta, and the r instead of r is going to be the radius of curvature, right? Now, if we take the time derivative, right, the time derivative of this equation, we are going to get ds over dt equals, why is rho not there? Rho is a constant, so a constant can be placed at the front of the equation. Why is rho a constant? You know, the radius is always the same. So we will get s dot, it's a time derivative notation. S dot equals to rho times theta dot. Now we can rearrange this to become theta dot equals s dot over rho. And that would equals to, remember what s dot is? Which is velocity, right? So it's going to be velocity over rho. So you plug this expression into this equation, then you will get acceleration equals v dot u sub t, the unit vector, plus v times v over rho, right? Theta dot is v over rho. So v over rho times v is equals v squared over rho u sub n, the unit vector in the normal direction. There you have it. The magnitude of the tangential acceleration, which is v dot, and the magnitude of the normal acceleration, which is v squared over rho.